Okay, we are live. That's great. So, welcome everyone to Climate Chat. I'm your host, Dan Miller, and today we are going to be discussing James Hansen's recent um, update on global warming acceleration. And we have a very special guest to help us with that. That's Leon Simons. Leon was one of James Hansen's co-authors of the groundbreaking study last year called Global Warming in the Pipeline. And this update is sort of an update to that paper. Let me stop sharing and welcome Leon to Climate Chat. Thanks for being with us again. You've been with us several times, and we really appreciate your joining us because actually Leon is one of the folks who knows perhaps the most about the subject of how emissions from ships can impact the climate. And that's going to be a theme of what we're going to be talking about today. There's a lot of scientific debate on this subject. In fact, was it last week we were interviewing Gavin Schmidt, who heads the Goddard Institute of Space Studies, which James Hansen used to run for many, many years. And then when he left, Gavin took over. And Gavin, is one of the climate scientists who thinks that emissions from ships can't have that much of an impact. This is going to be a key point we're going to be talking about today. Anyway, Leon, thank you. Welcome to Climate Chat. Oh, now I'm not hearing you. Oh, we had you on before.
No, it's okay. I just
Oh,
had
there we
to
go.
switch on
Okay.
now. Hi, thank you
Okay.
for having me on your show.
That's great. So what we're talking about today, and this is all in the show notes for YouTube and also on Clubhouse if you're listening there. The title this is was released on May 16th, and the title of the update is Comments. This is from James Hansen. Comments on global warming acceleration, sulfur emissions observations. And there's a link to that in the show notes there on the YouTube. So if you want to read it yourself, you can. I also did a Twitter summary that highlights the key points. And if you go to @DanMiller999, then you can find that as well. And but we're going to get into depth into this report today. So, and in fact, Leon was tweeting about some updated information that's really kind of mind blowing that we're going to jump into. But basically, I just want to sort of highlight why this is important, what we're talking about, and why this is important, and why this is going to affect everyone's lives. This is not like some academic exercise like what's the radius of a black hole or something like that, where whatever the answer is, it doesn't change much. This is something that is not only can affect our lives, is affecting our lives right now. And by that, I mean global warming, which, we all know about, has been rising steadily from the 1970s to about 2015. In other words, it was going up at about 0.18 degrees Celsius per decade, or call it, 0.2 of a degree per decade. But then something happened. Something happened around that time where all of a sudden they were good. Thank you for that. So around 2015 or so, the temperature started going up more quickly. And there's a question like, why is that? Why did it go up more quickly? Well, James Hansen, Leon Simons, and others wrote a paper last November. It was actually worked on for a very, very long time, but published last November, that suggested that one of the main reasons why global warming is accelerating is that we're changing the aerosols that humans put into the atmosphere. So what's aerosols? Aerosols is kind of a fancy name for smoke particles, particulate pollution, sulfur emissions, that kind of thing. And that is given off by coal plants and cement plants and ships and cars and all that kind of thing. But as you can see in this picture that Leon's sharing with us, you'll see a lot of the emissions are coming in the North Atlantic and North Pacific region. So what's happening there? There's a lot of shipping traffic. In other words, ships create a significant amount of sulfur emissions. But something happened starting in, I think it was 2015, Leon, correct me if I'm wrong, where the International Maritime Organization said, you know, pollution from ships, sulfur pollution from ships is very bad for human health. So we're going to regulate that. We're going to tell all the ships that they have to start reducing the sulfur content of the fuel, the oil essentially that they burn for the ship. And starting in 2015, they have to lower it. But then in 2020, it has to be, I believe, 80% lower than it was originally. And there's a popping this up.
Yeah,
And
so the
want to keep
regulation was
going? Go
introduced
ahead.
in 2008, and then regionally there were already some lower sulfur fuel regulations in place, and they got stronger in 2010.
Okay.
And then globally, they got a bit tighter in around 2012, but
Well,
most
okay.
ships were already adhering to that. And then in 2015, in these regions in the North Sea and around North America, the sulfur fuel content was reduced from 1% to 0.1%. And then in 2020, the global sulfur fuel content and the maximum allowed sulfur fuel content was reduced from 3.5%, so that's outside these regions, to 0.5%. And that, of course, decreased sulfur emissions globally by a significant amount.
Yeah. And so the sulfur emissions went down dramatically. So that's good. That's good for human health. Everyone, that should be the end of the story. But it wasn't the end of the story. Because something that happened at the same time is that global warming, which was, of course, global warming, the world was getting warmer every year on average because we continue to put more greenhouse gases in the atmosphere, and the greenhouse gases act like a blanket. You've probably all heard this, and hold in the heat and warm up the earth. That's one part of it. But the other part is that the earth is also cooled by these sulfur emissions. They help both reflect the sun away directly because it's sort of like a white cloud itself, but more importantly, it forms the nucleus for water droplets to form clouds. So it forms clouds, it makes clouds brighter, and it makes clouds last longer. So all of those things help reflect sunlight away from the earth and keep it cool. And not by a little bit, by a lot. In other words, we are currently, by accident, because this, we're not intending to cool the earth by our ship emissions and coal plant emissions and pollution from our industrial sectors, but it is cooling the earth. So we are doing what's called sunlight reflection methods or solar radiation management or solar geoengineering. We're doing it on a massive scale today, but we're doing it by accident. And now that we're starting to clean it up, we're starting to see the impacts of that. The world is getting warmer. But the debate really is, well, wait a second, but emissions from ships are very tiny compared to all the other emissions that we do, and even the pollution emissions. And so how could that be that the world is warming because we're reducing the ship emissions? But the interesting thing is this International Maritime Organization, the fact that they made this change and we're seeing the change in global warming, it's an experiment, an unintended experiment, but an experiment on a grand scale that is teaching us more about climate change than we knew before. And this is what James Hansen and Leon Simons spoke about in their Global Warming in the Pipeline paper. And that is what this update is all about. So I wanted to set the stage. And the reason one of my favorite quotes about climate change is from Tom Friedman, and it goes like this. It says, "You may not be interested in climate change, but climate change is interested in you." So whether you're interested in climate change or not, the discussion we're having today about the impact of ship emissions on climate and the acceleration of global warming will affect everyone on the planet and certainly affect your children in a big way. And so that's what I wanted to do to set the stage about what we're talking about today and why it's important. So with that, again, there's a link to the report. And then if you could pop up that global temperature graph to start with, maybe I'll just say a few words about it, and I'd like to turn it over to you to get your comments on that. So the report starts off with this, and there's some really interesting things. I guess you're sharing, so I don't know if you can see my pointer there, but on the you can see the green line is sort of the linear fit of how temperatures were going up from 1970 to 2010. And you can see that the black dots are the yearly averages of temperature. And you can see that the black dots, around a little bit before 2020 and on from 2015 onward are mostly above the green line. And the green line is supposed to be the average. So you should be seeing dots above and below. But since most of the dots are above, that means we're no longer warming at the green line level. We're warming what sort of this yellow area, which is what Dr. Hansen and Dr. Simons predict will be the acceleration in global warming. And take a look at that very last dot. That's the black dot. That's from I guess that's 2023 at the Goddard Institute of Space Sciences prediction of temperature. Everyone calculates global temperatures a little bit differently. Berkeley Earth had us above 1.5 degrees. This is slightly below 1.5. Again, they just do it a little different. They have different reference temperatures and things like that. But take a look at the blue line. The blue line is the 12-month running mean. In other words, the last 12 months. And you can see we're still zooming up in temperature. And the reason for that is that we have an El Nino. And in the update, Dr. Hansen predicts that the temperature will keep going up for a month or so, or maybe a few months, and then start heading down as we switch from a warming El Nino to a cooling La Nina, which is a cycle that goes up and down over time. And it's not really what forces the temperature upward on a long-term basis, only on a short-term basis. So that's pretty dramatic temperature we're at right now, above 1.5 degrees, even on the GISS model. So Leon, what thoughts do you have on this?
Yeah, so it's now, I think it's now 1.56, and it should keep going up at least in May, and it depends, of course, a bit how warm the next months will be compared to 2023, because 2023 was, of course, also very warm. But May is expected to be warmer this year than last year, so this line will keep going up for at least one more month. But indeed, that's a variability, and that's a global surface air temperature, which is, of course, it's interesting. But in my opinion, the more interesting is what's happening in the oceans, because 90% of the heat goes into the oceans. And also the data showing why this is. So if you like, I can already
please take us through that. Yeah, please take us through that.
Because of course, let me show you the graph. I did just some news. So this line, the pink line is this year, and the red line was last year for the North Atlantic Ocean. That sea surface temperatures anomalies compared to the 1982 to 2011 average. So how these are all years, all these lines are years, and the red line is last year, and the pink line is this year. And last year this graph went viral in media and social media, but also in more traditional media around the world. And that was at the point when it was about here. And now we are again at the same point, or even higher than when this graph went viral around the world. And and this is really, I think, more important than the global average surface temperature, because this is the ocean. It's an ocean area of 40 million square kilometers, and it takes 3,000 times as much heat to warm seawater than to warm the same volume of air. So if this line increases, it's now about half a degree warmer over 365 days average than any year before. So that's really an enormous increase in sea surface temperatures. And of course, this is the ocean where many of us live and grow our food, and where hurricanes form. So this is, and where much of our weather comes from. Living in the Netherlands, of course, we have wind coming from the west, so a lot of water coming from the west. Last year was also the wettest year in the Netherlands ever in observational history. So this is these graphs are, we don't share this just to scare people. It's really crucial information to understand what's happening.
Mm-hmm. There's like nothing like that. I mean, by the way, so, and it's your, your prediction and Hansen's prediction that a big cause of this dramatic increase in the North Atlantic Ocean temperature is due
I'll
to
get to
the,
that.
okay, right, all
Yeah,
right.
so now we're going, so models before the regulation, which you already talked about, before that regulation came into effect, models showed that over the North Atlantic and North Pacific Oceans, where most of the shipping happens, there would be the biggest effect on how much radiation is absorbed from the sun, which makes sense because that's where the particles are being emitted over the dark oceans. And if you have less bright particles and additional clouds reflecting sunshine back to space, there's more sunlight being absorbed. So that's what the models showed. The many different models show that with a lot of uncertainties. And now, as you mentioned, we have this natural experiment, which is crucial because the largest uncertainty in climate science is what the effect is of aerosols. So this is a crucial natural experiment to try to understand better what's happening in the real world, because models are just models, right? Mm-hmm. And what we see that over the period that these emissions were decreasing, and that's not just from shipping, that's also from Chinese coal plants installing these desulfurization systems, taking the sulfur out of the emissions. The United States stopping fracking for natural gas, and then closing the coal-fired power plants and using gas-fired power plants instead, reducing also the particulate air pollution. And then you see that over the last decade, but especially since 2020, since this global shipping regulation came into effect, there's a lot more sunlight, solar radiation being absorbed over the northern hemisphere mid-latitudes. This is absorbed solar radiation relative to the first 10 years of NASA.
Yeah, maybe let's talk about what this graph shows, because I think if people looking at it for the first time might get confused. So there's time is on the bottom.
Satellite data from NASA showing they look at how much sunlight is reaching the planet and how much is being reflected. And then if you take what's coming in, you take from that what's being reflected, you have the net absorbed radiation.
And the vertical axis is latitude. So you're sort of taking all of the absorbed solar radiation at that particular latitude. That's the point at a particular time. That's the point on the graph. And so the dark red shows that in the northern latitudes, where the North Atlantic Ocean is, there's a lot more sunlight being absorbed, but the same thing's not happening in the southern region. So there's something asymmetrical there. So maybe something's happening only in the northern side that it's not happening in the south. Yeah.
And indeed, we compare these regions.
Yeah. So that's like a clue to what's happening here.
Yeah, exactly.
Okay.
Remove that.
Okay.
Yeah, so in these regions, we see that more sunlight is being absorbed, and here we don't see it. And then, of course, you see El Nino. Here, especially in this region, you see that because there was La Nina the past years, there was less sunlight being reflected to space. Because the colder oceans, there's more clouds forming over the colder oceans. And that means that because then there's more cloud formation. We see that in the Netherlands, for example, in winter we have much more cloud formation than in summer, for example.
That's a point I didn't realize. That's a very good point.
Yeah.
Okay.
And that's translating also to, of course, this you see again the La Nina. And here,
well, again, let's tell people what this chart's different. It looks similar in many ways. The last chart was about how much sunlight we were absorbing at different regions of the Earth. This chart is about the sea surface temperature. Is this just ocean temperature?
Yeah.
So the surface of the ocean temperature, not the amount of sunlight being absorbed. This is the actual temperature of the ocean. Go.
Exactly.
Okay.
And then you see the La Nina, which we had 2 or 3 years of La Nina. You see that the ocean was relatively cold during La Nina. And then El Nino periods, here you see 1997 and 1998. You see here El Nino in the Pacific forming. Here the small, less strong El Nino. And here again in 2015 to 2016, you see in the tropical Pacific, you see the effects of El Nino. And now we see it also here in 2023. And of course, now we're going into 2024, so the data is not shown here yet. But here in 2020, from 2020 onwards, you see that the sea surface temperatures at the higher latitudes, where most of the ships are transporting goods between China and North America, and between Europe and China, between Europe and North America. That's where you see that the oceans are warming very rapidly. So I'm often asked, so why do we only see it now in 2023? But that's not the case. We already saw it. But globally, we didn't see it in the global surface air temperatures or the sea surface temperatures that clearly, because that was more or less hidden by the 2 or 3 years of La Nina.
Right. So the La Nina, which was cooling the sort of the central latitudes there, as you can see, was offsetting the warming that we see in those northern side. But so that gave us global temperatures that didn't look exceptional until recently, when that central latitude thing switched from La Nina to El Nino, and that part got warm too. And that's when the warmness of El Nino added to the warmness from the shipping changes, or that's what we think it is, in the northern latitudes. And then you add those together, and all of a sudden we had a boom, a dramatic increase in temperatures in 2023.
Yeah, and this is global surface temperatures.
So this is ocean and land together.
Yeah, just global surface temperatures. Yeah, and then you see that indeed here the effects of La Nina cooling, and then the warming El Ninos. But you see here again the effects of not just shipping but air pollution reductions already also from China and from North America happening already before this regulation came, global shipping regulation came into. And then that's so we don't know how big the effect is. The data is now coming in, and it's a crucial forcing to take into account when you want to understand what's happening. Because maybe it's good to explain a bit what's driving the global climate. And of course, that's the sunlight coming in. So what happens to sunlight reaching Earth? So about 30%, 29% of the sunlight is being reflected to space. And this region shows absorbed solar radiation. and also outgoing long-wave radiation. Because if you look at the scale, it is in watts per square meter. So the global average in watts per square meter. So you have an area of 510 million square kilometers. Then over this whole area, that's how much sunlight is being absorbed. But if you look at it from this with this large axis, it's about almost the same amount is being radiated back to space as infrared radiation, as heat.
Right. So just to explain that to everybody, the sunlight comes in, shines on the Earth, it warms up the Earth, and then the Earth is warmer, and it there radiates heat or long wave radiation out to space, and that's what helps keep the Earth in energy balance.
Exactly.
But of course, when we put more greenhouse gases around the Earth, it allows the sunlight to shine through them. It doesn't stop sunlight, but what it does block is the heat radiation from the Earth coming out into space. It traps more of that than it used to, and that's why we have global warming.
Yeah, and the sunlight, the how much sunlight is coming in, this is over the past 20 years, and this is a 4-year average to reduce all the variability, the weather, let's say. And then you see that this doesn't change much. Now it's at a peak at the highest level it has been in the past 20 years, but that doesn't change much. But the amount of this in yellow, you see the amount of sunlight that's absorbed, that has increased a lot more. But even the outgoing radiation, radiation in long wave and infrared has also increased. And you might think that doesn't agree with the, let's say, hypothesis of greenhouse gas absorbing outgoing long wave radiation. But that's a logical first thought someone might have. Mm-hmm. And that's also many climate scientists also think this is decreasing because of that. But in fact, it's increasing. But relative to how much sunlight is being absorbed, this is decreasing. So there's relatively more sunlight being absorbed, heat staying in than there's sunlight being absorbed.
Right. Now,
okay, and that causes there more heat to accumulate in the Earth system, and that now that has more than doubled, even tripled. If you look at this is the past 4 years, and this was the first 4 years of of data. But it has more than tripled the amount of heat that's accumulating in the Earth system. Has more than tripled, and how that develops, of course, we don't know. But this is very worrying. This is really very worrying, because this is climate change. So how much heat is accumulating in the Earth system, and then where that goes into heating the oceans, into melting ice, into heating the land, into heating the atmosphere. That's important, of course, but it starts with how much heat is accumulating.
And even though people don't understand what watts per square meter means, 1.4 watts per square meter, that's on the order, the energy equivalent of about 1 million Hiroshima atomic bombs exploding every day.
Yeah,
I mean, so I think a little more than that, actually, but around 1 million every single day. That's how much that energy that's heating the Earth represents. Because when you just talk about watts per square meters, it doesn't sound like very much, but there's a lot of square meters on the Earth. And so when you add up all those watts, it ends up, it's really a huge, huge amount.
Yeah, it's an enormous amount. And with this large axis, you might wonder if this is a lot, but you also, if you look at the Earth's temperature, you also have to look at it from the perspective of Kelvin, degrees Kelvin, and then you have the same effect. And if you look at this, the temperature in Kelvin, about 1 compared to how much sunlight is being absorbed, 1 watt per square meter translates to about 1.2 degrees Kelvin or degrees Celsius, which is the same. So if you have one, so very roughly, just for your understanding, if you have 1 watt per square meter additional heat accumulating, that could translate to about 0.2 degrees Celsius of warming.
Mm-hmm.
So this
And
really,
every degree of warming is a huge deal. We've already now experienced about 1.5 degrees recently, and it's not linear. So as it gets warmer, more and more things break down. In fact, I still remember from 2010, we interviewed climate scientist Kevin Anderson again recently for the second time. And I first learned about him in 2010. And what he wrote then, he said, well, what does 4 degrees of Celsius warming mean? And he said, it's not compatible with an organized global community. So that was the first thing about it, which, when you really think about what that means like collapse of civilization. He said it's also beyond, it's devastating to the majority of ecosystems, and it's beyond adaptation. So we're not going to just like turn the air conditioners up and be fine. And the last thing he said is that it's not stable in the sense that 4 degrees will lead to 5 and 5 degrees will lead to 6, for example. So we're not there. We're not at 4 degrees, but that's
yeah,
the
but
direction we're
it's crucial to
heading. And
understand because this cooling effect,
yeah, go ahead.
it, it, this cooling effect happens mainly where we live and where we grow our food.
Mm-hmm.
So all this air pollution was cooling, and still there's still a lot of air pollution, and that's still cooling the planet relatively to how fast it would be warming if there was no air pollution. So
Mm-hmm.
this air pollution is still was mainly cooling and is still mainly cooling where we live, where we grow our food, and now we have stopped polluting, and that causes, we call that an aerosol termination shock, because you terminate the emissions, and that causes a shock of very rapid warming, and that's especially where we grow our food. So that's a crucial aspect of what's going on.
Well, I think you're also making a really important point, because when we talk about greenhouse gases like CO2, those are called well-mixed gases. So it doesn't matter where you release them, they end up all over the world, like distributed around the world. But cooling aerosols or pollution has more of a local. You emit it, it only stays in the atmosphere for about a week. It doesn't spread all over the world. So it acts as you can kind of think of it as like a little umbrella blocking some sunlight for you in the local area where you're polluting. So when you get rid of it, you have the biggest impact happens where you were polluting.
Yeah.
As opposed to globally. Yep.
Yeah. So I don't know if you want me to go into more detail about forcings and about.
Well, why don't we go through a little bit of what's in the update, and then when you see things that make sense to expand on, we can do that. So I made a bunch of basic points about what, and I'll just read them out here, and you can. We talked about some of them. So one point that it was in this update from James Hansen is that the 12-month global temperature in April was 1.56 C above the 1880 to 1920 temperature average. And this is, again, using the NASA approach to global temperature measurement, or the GISS. And he then said the temperature will likely rise for at least a month and then drop as the El Nino turns to La Nina. We talked about that a little bit, but then he goes on to say, he said that acceleration of global warming is now hard to deny. So not global warming, but the acceleration in global warming. We're now getting warmer faster than we were in the 1970 to 2010 timeframe. It's now, he said the 12-month temperature is now 0.36 degrees Celsius above the 1970 to 2010 trend line, which is 3.6 standard deviations. We don't have to get into the details, but that's sort of a measure of how far away from the mean you are, and that's so far away from the mean that the chances of that being sort of a natural variation is like less than 1%. So in other words, the confidence that the temperature trend is accelerating is greater than 99%.
I don't think
But go
there's
ahead.
many people anymore saying that there's no acceleration. Or there were
Right,
some in
but they're
denial.
disagreeing about why. But yes, I had
No, I think even most agree why or what
really,
contributes. I think most say, okay, the greenhouse gases are increasing,
yeah,
aerosols are decreasing, and that's causing accelerated heat uptake and increased rate in global surface warming. And the question is, how much? That's the biggest. That's the real question. And we're only getting the data now, but to answer that question, because until now we mainly had models, which were based a bit on real world data. But of course,
mm-hmm.
this is the first time we have such a large experiment from one day to the next, virtually reducing emissions over a very large area of the globe by such a significant amount. And
Right.
with that, we can reduce this very large uncertainty within climate science.
Right, but the big question mark, which you're alluding to here, that you covered in the global warming in the pipeline paper, and which this update also addresses, is that the big, I would say, the sort of the headline new information that was in the global warming the pipeline paper is that Hansen and you and your co-authors believe that the IPCC, or the International Panel on Climate Change, did I say that right? Is wrong in two respects about global warming. One, that the warming from greenhouse gases itself, like CO2 and methane and all that, is, you guys are saying it's more than the IPCC assumes. The IPCC uses different models, but most of them assume that a doubling of CO2 would lead to a 3 degrees Celsius increase in temperature in the quote short run. We don't have to get into the
I
details
think
and
that's the
exact definition.
average.
Yeah, that's the average, but sort of 3 degrees. And then there's some above, some models are above and below, but the IPCC is sort of at the 3 degree number. In your paper, you say, no, a doubling of CO2 leads to a 4.8 degrees Celsius increase in temperature, which is a huge amount more. And what that means, and then the second thing, before we talk about what that means, the second thing that's in your paper is that you are saying that the cooling we get from the aerosols is also much more than the IPCC assumes. So IPCC assumes there's like this much warming and that much cooling, and that gets us here. And then in your paper, no, there's this much warming and this much cooling, and it still gets you to the same average, because the more warming and more cooling cancels each other until you start cleaning up the aerosols.
Yeah,
And
they'll
so
stop
your
cooling.
prediction in your paper is that the warming we should expect as we clean up aerosols will be much more than what the IPCC used to assume. Is that a fair summary?
Yeah, so I think I think you said you predict or you think. It's like we don't think. We assess the data and we present the data. And I think that's crucial because there's a lot of thinking happening and a lot of people say, for example, also when we published the paper, there were a lot of comments from people who hadn't even read the paper saying, I think they are wrong, without addressing the data we present. And it's the data which implies that there's a stronger cooling effect from aerosols and the more warming effect from greenhouse gases. Um, and that's quite important to understand because we are now at a concentration of greenhouse gas. If you take all the greenhouse gas into account, that's more, that's higher, I'll show it, than it was during the past, then it was negative in the past 130,000 years. Because if so, so the greenhouse gas forcing. So how much are the greenhouse gases pushing the climate in a warmer or in a colder state? And that's compares it. We compare it to the 1750 average, which is pre-industrial, which is the same as IPCC uses. And then you see that the most negative the greenhouse gas forcing was because there was less methane, there was less CO2 in the atmosphere, less N2O. There was minus 3 watts, so there was more heat was radiated to space because there were less greenhouse gas in the atmosphere. We have now added so much greenhouse gas to the atmosphere that we've caused a greenhouse gas forcing of 4 watts per square meter. Of course, the planet is different from what it was during the last glacial maximum. Then the sea levels were 130 meters lower than they are today. There was a lot of
400 feet lower than they are today.
400 feet
meters.
About, yeah.
Yeah, amazing.
And much of that ice was situated on North America and Europe and Asia. And of course that was reflecting a lot of sunlight back to space as well. So you have to take these things into account. And that's also why there are many uncertainties, because now if you have a warmer world, as I already mentioned, there will be more effects on clouds. So there's cloud feedback, which cause more warming. And then indeed, if you look at this, what you call Earth climate sensitivity, if this effect is stronger, so if the climate is more susceptible to the cooling effect from aerosols and from the warming effect of greenhouse gases, then if you look at at this graph, if you look at if the Earth climate sensitivity is 1.2 degrees Celsius, there was more cooling, so about 1.4 degrees Celsius of cooling, than if it would be 1 degree, for example. Then there would be about 1 degree of cooling. And then also, if you reduce these emissions, of course, there will be less cooling. But not that doesn't mean that there's warming from these aerosols. There's less cooling, so the temperature is decreasing less. And that also depends on the Earth's climate sensitivity. If there's, then it could stabilize, and when you start reducing the aerosols, you significantly, then you could see more rapid warming, and that's what's happening now.
So I have a question for you on this. There was a recent paper that came out, and I don't remember, I mean, fairly within a month ago, where they said they looked at I think the same data. I mean, this ice age data, and they came up with an ECS, or Earth climate sensitivity, that they said could not be 4.8. And we're looking at, I think, similar data. They came up with the conclusion in their paper that the ECS was not that high. Did you read that paper, and you have thoughts on that?
I think that's a very interesting study. I think that what they mainly looked at is at the climate from the past glacial period. So why was it that cold? That's what the assessment focused mainly on. Why was it that cold? And that was what they showed was that because there's these ice sheets on the northern hemisphere, there's cold wind blowing also over the North Pacific and the North Atlantic, cooling the North Atlantic and the North Pacific, and that causes sea ice. And of course, sea ice also reflects sunlight to back space, but it also causes cooler oceans, which show more cloud formation because there's there's faster condensation, and these clouds also reflect sunlight back to space. And that was a feedback what we call negative feedback causing more cooling, and together that caused a cooler planet. Now, what they did was they used that estimate and that research to calculate. They put that in the model, and then they said, okay, if we put this in the model, we predict that the planet will warm, I think 3 or I don't know the number by heart, but indeed less than what we show. So they mainly look at it from that perspective. What we did was we look at it from, okay, how cold was the planet at that time, but also, okay, what was the climate like tens of millions of years ago? We look at it from the Holocene, when we see, okay, the CO2 and the greenhouse gas concentration was going up, but the planet was not warming, but was even cooling. So you might think, okay, that shows that maybe the effect of greenhouse gas is not that strong. Then we say, okay, you should also take into account pre-industrial aerosol. All these millions of wood fires and slash and burn agriculture put a lot of aerosols into the atmosphere, causing cooling, especially of the northern hemisphere. And that's also what the proxy data shows. So they look at the data from tree rings and from sediments from lakes and oceans and many other places, from corals. They show that there was cooling over the northern hemisphere while the greenhouse gas concentration were increasing. And we say, okay, that should we presented in our last paper the hypothesis that this could also partially be caused by the increase in these aerosols. And then what we also did,
well, and they didn't take. Just to be clear, you're saying that you looked. I remember, that you looked into that and you made those comments that, and again, this is pre-industrial revolution.
Yeah.
Burning of forests and clearing land and causing smoke in the atmosphere that would cool the earth. Are you saying that this other paper didn't take that into account?
No, I don't know of any paper that takes that into account. There's a hypothesis,
and that could be maybe the reason why they thought ECS was lower.
I'm saying that you should take all these lines of evidence into account, and then also the current climate. And if you look at the current climate and you think that shows that the greenhouse gas forcing causes less warming, then you have to. What's crucial is, okay, how strong is the aerosol forcing?
Cooling, right? Yeah.
How much are aerosols cooling the planet? You need to know that to be able to assess how much warming would be caused by these greenhouse gases. And then I think that, so from that all these different lines of evidence and more brought us to the Earth climate sensitivity we presented in the paper. But for me, like it's interesting scientifically. It's interesting, but we will never know the answer to this question because we will never have a greenhouse gas concentration which is stable at 4 watts per square meter, which is what the Earth climate sensitivity is, which you double the concentration of CO2, you keep everything else stable, and then you look at what happens to the climate within 60 or 70 years, and that's the Earth climate sensitivity.
Right, these are scenarios; they're not predictions.
No, right. and that also depends on many different. We had a climate in the Eemian last warm period before the last ice age, before the last glacial period. Then the temperatures were already as high as they are today, and the sea levels were 5 to 7 meters higher than they are today. So even with much less greenhouse gases, we can have a warmer world. To me, that just shows that it's not static. It's not one answer. It's just if you take a climate model, but we don't live in a climate model. We live in a world where we have increased the greenhouse gas concentration now by about 2 times CO2 if you take all the other greenhouse gases into account, and we cool the planet.
By the way, to be clear, 50. We've actually increased CO2 concentration in the atmosphere by 50% from 280 to 420 parts per million. But when you add other man-made greenhouse gases like methane, nitrous oxide, and all those other, you add those all together and look at the forcing or the amount of the warming those gases cause, we're really at an equivalent of a doubling of CO2.
Yeah.
Okay. Just wanted to make that clear.
I wasn't sure if I should. It's a bit technical, but this is the total greenhouse gas effect pushing the climate into a warmer state. Oh, sorry. And that's now about 4 watts. So this is the IPCC data.
Mm-hmm.
And then the aerosols are causing cooling with very large uncertainty, which is not shown here. And then the net effect of these two is shown here, which is now, according to the IPCC, about 3 watts per square meter. But it could also be 2 watts per square meter if this is more negative, or if it was more negative before the shipping regulation came into effect. And then, because then the net of so let's assume that then the current warming is caused by only 2 watts per square meters of net forcing.
Mm-hmm.
And then we still have an imbalance, this is the energy imbalance of how much heat is accumulating, how fast in the system, which is increasing very rapidly. This is the NASA data I showed you before. And we still have an imbalance while the temperature globally is now about 1.4 degrees Celsius, again, according to the IPCC, above 1750 when the Industrial Revolution started.
Mm-hmm. Mm-hmm.
So then it's important to know what climate forcing caused the current warming. That's crucial, and this
Right.
uncertainty is crucial. And that's also part of the answer. If you say, okay, and many agree on that. I think most climate scientists agree. If aerosol cooling was stronger, then there will be more warming if we reduce these aerosols, even if we would also decrease greenhouse gas concentrations, which we are not doing.
But I think one of the key things in this update, which is mentioned in previous updates, and this is kind of a mind-blowing thing, there is a very big disagreement on how much impact shipping emissions causes warming. And as it says in the update, let's see, where is that part?
Yeah.
Hansen and Leon Simons estimate the impact from the International Maritime Organization reduction of ship aerosols is 10 times more than the IPCC estimates. And I think in particular, you're talking about Zeke Hausfather, who we interviewed, by the way, a few weeks ago, about all things, but we talked about this too. And so that's not like a little subtle difference. Is this 1.6 instead of 1.4? We're talking about a 10 times difference. Can you maybe just talk? I mean, that's such a. And then, by the way, Hansen goes on to say, which is, I think, a really interesting thing. He says the difference is so large that it should be clear who is correct in the next few years.
Yeah.
So maybe you could talk.
Yeah.
That's
So
such a huge
what
difference.
they do.
Can you talk about that?
I think that's what I said. It's the uncertainty is so large, because the aerosol, the effect of aerosols is very uncertain, and that's so what they did was they took a simple climate model and they reduced global aerosols. Let me share this screen. They reduce global aerosols or sulfate. They reduce global sulfur by 80%. But as you see, shipping, see my mouse?
Yeah.
Shipping doesn't happen over globally averaged. The ships are not on the land, right?
Mm-hmm.
So you have to take into account that the ships are not over land, that the ships are over the oceans. If you don't take that into account, your answer will be wrong because your assumptions are wrong. It's quite simple. So So the climate models are wrong. Every model is wrong, but these are very wrong because the assumptions are wrong. So they cannot be right. Even if the outcome would be right, they were right for the wrong reasons.
Okay.
And that's crucial to take. This is really crucial to understand. And other things to take into account are how long do these particles stay in the atmosphere? How much of the emissions is sulfate instead of sulfur dioxide? How much is reduced? How much was being emitted before this regulation came into effect? So, how strong is the effect on clouds? How much sunlight do they reflect back to space? How much heat radiation? It's like, do they also act like greenhouse gases, radiating heat back to the surface? All these parts should be taken into account, and they are very uncertain. We don't now know how much sulfur algae put in the atmosphere because we don't know algae, because algae also emits sulfur. And if you the assumptions you take about algae are crucial for the outcome of your model. And all these other things are also so. That's why when Jim says, okay, we will learn from the data, that's what he says. We will learn from the data what's really happening. And that's what we're now starting to learn. If you see, if I take this region, so again, most of the sulfur was being emitted, from shipping was, of course, it was also in the Indian Ocean and here around Australia and in the southern Atlantic, but most was being emitted over the North Pacific and the North Atlantic Ocean. And then if you look at this region, combined region of North Pacific and North Atlantic and North America, and we see in the past years that that there was a very big increase in how much sunlight was being absorbed. And that explains about 77%. Then we see if we look at that again, here's the shipping in global shipping emissions in 1,000 tons. And this is the absorbed solar radiation normally from the first decade of the satellite data. Then you see that 4.3 watts per square meter over this enormous area of over 11% of the Earth's surface. 4.3 watts per square meter more sunlight was being absorbed in 2023. And again, that's as much as all the greenhouse gases together cause for warming globally on average. And this is for this region. But it's the same amount, same order of magnitude. So even if this was the only region, if this is the amount, okay, let's assume, if it's 4 watts per square meter, then it's over. Then it's, I think what Hansen wrote in his mailing now was about half a watt of forcing globally caused by the reduction in shipping emissions. Only if this is almost already 0.4 watts per square meter, right? Or just looking at solar, but for only 11% of the surface. And then if we look at the global data, we see that this energy imbalance has increased by about this amount globally average, because you also take into account that more heat is radiated to space as the planet is rapidly warming.
So by the way, so there's this 10 times difference. As you said, a lot of it's maybe because of the model is wrong, but my understanding of what they're getting wrong is they're just saying, look, shipping emissions is only a tiny percentage of global particulate or aerosol emissions. And if we just, look at the ratio, and then we just look at how much shipping emissions was reduced relative to all of the sulfur emissions that we are emitting, the amount is tiny. And so on a global basis, that should be this much warming, that 1/10 of what you say it is. But when you look into the details that you just went through, some of the differences between sort of taking the simple-minded approach or simple approach and the more detailed approaches, you say, well, wait a second. It's not just the sulfur emissions themselves that are reflecting sunlight. they cause clouds to form, and that's like an amplifying effect. Plus, they're making these clouds over the pristine ocean, and underneath that ocean is dark blue, which absorbs like 80% of the sunlight that hits it. If you put a cloud on top of that and reflect 80% of the light, that's a huge difference. Where if you do the same thing, let's say over China, where they're reducing their pollution. Well, first of all, China's not dark blue underneath, and so it doesn't absorb as much anyway. Plus, there's all this other pollution going on there. So even if you reduce coal pollution, there's other kinds of pollution. So those differences, when you really get into the details, as you were just alluding to, can cause not just a little difference in the amount the world warms, but in this particular case, a 10 times difference from that simple model. Maybe, I guess. We don't, as you said, we don't know. We're going to see over the next few years how much the world warms.
Climate models which looked at this in detail show. So it's not something. That's also something what the models which look at this in detail, they also show an effect of about 4 watts or 0.4 watts globally, and especially in regionally up to 10 watts per square meters over certain parts of the Pacific, especially in the eastern part of the Pacific. I compared it. I made a bit of a joke, but I said the statistician drowning in a river that's on average 1 meter deep.
Right.
Yeah. And because it's really the wrong way to look at it, and Gavin even called me an ass because of that when I said that. But it's we present the data, and if someone doesn't show, I respect them because of course they are on the forefront of this global system modeling, and they are contributing a lot to the science. I respect that very much. But we shouldn't underestimate the regional effects. Let me show one slide again. Yeah. Indeed, because the Earth is about 70% of the Earth is covered by oceans, and 90% of the heat accumulates in the oceans. And then if you reduce the sulfur emissions over these dark indeed oceans, dark and cold oceans, by 80%. This is not simply saying, okay, we just reduce it by 10% globally, because that's completely wrong. That's just that doesn't mean anything. If you compare it to a global average, that doesn't tell you anything. You really have to take this very simple fact into account, that 70% of the world is covered by oceans, 90% of the heat of the energy imbalance is going into the oceans, and 80% of the sulfur over the oceans was reduced. And then you can start trying to understand what's happening, looking at the data. Of course, these climate models are interesting, but without the data, you cannot learn a lot which we don't already know. We already know that the effect is between 0 and a half or 1 watts per square meter. So
how long before you think this issue is settled? Hansen says a few years. Do you think a few more years of data is going to make it very, very clear how much of the acceleration of warming is caused by shipping?
Some say the science is never settled, and it's so what it's almost a philosophical question, I think. So how much cooling were these aerosols causing? How much warming are greenhouse gases causing? If you reduce aerosols, is this warming which you then would then see, is that caused by the decrease in aerosols, or is that caused by greenhouse gases? Which greenhouse gases? Is that caused by methane, or is it caused by CO2? Right? It's almost philosophical. Like if you would also reduce methane, you would not have that warming. Okay, is that then because of the decrease in methane? So it's also there's so much going on. That's of course, if you see the sea surface temperatures are increasing, are they increasing because the aerosols are decreasing, or would they have increased also without the decrease in aerosols? That's a difficult question to answer. Um, so and even if we think we can answer the question to a certain extent, others may not, right? So that's it's not just it's also partially perspective. And what we've seen, I think already since 1966, when James Lovelock was talking about, was looking at this as a cooling effect of sulfur pollution of air pollution from Shell. He was doing some research for Shell. He
Mhm.
was already told, don't tell this to anyone, don't discuss this with people outside Shell. And we've seen that a lot happening. We've seen that especially the past 4 years. As I mentioned, I've been called an ass. I've been called. I've been compared to deniers. I've been. We've been. Some have been insinuating we are lying, that we have some hidden agenda. So people really, it's the inconvenient, the mother of inconvenient truths. Even Al Gore didn't discuss this in his movie. So
Mhm.
and I think that's also a reason why many are hesitant to even discuss this or to put a number on it, which might be higher than their simple models show, but is more
Well,
close to what the data shows.
well, again, and as Hansen points out in this update, if indeed aerosol cooling is more than was thought, that implies that greenhouse gas warming is also more than was thought, and back to the original global warming, the pipeline paper, we're an ECS
Exactly.
of 4.8 instead of 3. And so those things go together. I want to cover a few more things that were in the update. I'll go through them briefly. And if you have a comments on them, please chime in. But one of the things he said was the current Earth energy imbalance. In other words, the amount of energy going in versus going out. That's the imbalance. And right now, there's more coming in than going out, and that is the thing that warms the Earth. The current, and it's called the EEI, the current Earth energy imbalance will limit the La Nina temperature drop that we're about to see following the current El Nino, so that the El Nino La Nina average temperature, in other words, the temperature kind of now versus the temperature after the Earth cools a bit with the La Nina. So that average temperature is likely to be in the 1.5 degrees Celsius range, according to Hansen. And he says that means that the 1.5 Celsius milestone is already reached. And he puts it for all practical purposes. In other words, we're basically at 1.5 C now. We'll know after the La Nina kicks in, and we'll see how much, because a lot of people think, oh no, the world's Earth's gonna cool a lot with the La Nina, like it did last time. And this is one of the data points we're going to know whether shipping really had a big impact, because that's the difference between like the previous ones and now. So that was a major point. I mean, it was kind of implied in the previous updates, but he made it, he said it in a very specific way. Um, and he talks about how the likely cause of the warming acceleration is a decrease of cooling human-made aerosols, which means our Faustian bargain. So Jim wrote a paper long ago called The Faustian Bargain, which is the deal with the devil. And he said the deal with the devil is that we're warming the earth using CO2, and that lasts in the atmosphere for hundreds to thousands of years. But we're offsetting a lot of that warming with cooling aerosols that last in the atmosphere for about a week. So when you finally stop emitting the cooling aerosols, he says the Faustian bargain will be due. You're going to have to pay the devil. And he's saying that is what's happening right now. It's not like he wrote that paper long ago before the payment was coming due. And he's basically saying that's coming due. I'm not sure if,
1990.
yeah. So I don't know if I have that link in the description, but I should put that in there. It is in my Twitter summary, is the link to the Faustian bargain paper. He also says,
Let me show it. It's at least
oh,
the
Well,
the
I can
slide.
also add it to the YouTube description later as well.
Yeah,
Yep, there it is.
I simplified it like this. So this is the deal with the devil, and the devil is like cheap oil, very cheap energy, and the effect is rapid warming on
Hmm.
greenhouse gases. But with this, with the burning of these fossil fuels, we are also emitting a lot of sulfur, and sulfur was cooling the planet. So now we are cleaning up the sulfur without addressing the greenhouse gas emissions, and that's causing rapid warming. And that's
Right.
already, Hansen already discussed that in 1990. And then he mainly talked about what will happen if we start reducing the use of fossil fuels. But we are not reducing fossil fuel use. We're still increasing fossil fuel use globally, but we are only decreasing sulfur. So that causes even more warming. And the worst case scenario we showed of the effect of this warming, or the initial cooling effect, that was the IPCC thinks now it's even more than Hansen presented there, and now the data is starting to show that it's likely even more than that.
Hmm. So one of the things we talk about on Climate Chat quite a bit, and we had guests to talk about what I like to call sunlight reflection methods, which is also called solar radiation management or solar geoengineering. And this is where we purposely put sulfur particles in the stratosphere instead. And that's just one. There's different ways to do this, but we're talking now about this particular method of putting sulfur particles in the stratosphere, where they last for about a year or so, not a week. And therefore, we had Doug McMartin on from Cornell, who's a researcher in this area. And he said, basically, we could reduce sulfur pollution in the lower atmosphere where we're currently emitting it, where, by the way, when it kills millions of people a year through health effects and things like that. And we could reduce that by 95%, take the last 5% and put it in the stratosphere instead of the lower atmosphere, and we'll get more cooling. So this is sort of purposely, we're artificially cooling the Earth. I'm sorry, we're accidentally cooling the Earth right now. And instead we could be purposely cooling the Earth, and it would be much healthier because you'd have so much less pollution, so much less people in breathing in this stuff. Do you have any thoughts on what your research shows? I mean, the research about the shipping emissions and all that, what the implications are for purposeful cooling of the Earth using aerosols?
One big thing it shows is that we can cool the planet, and that we have cooled the planet, and that the cooling and the time we bought with that, because that will be, I think, the reason to, is not being used to reduce greenhouse gas emissions. I think that's too important. That's crucial, because I think if you would do it on purpose, why would you do it? To buy time. Time for what, right? If you
Right.
make the problem worse, if you buy time to make the problem worse, which is what we have been doing, right? We bought ourselves a lot of time unintentionally by emitting a lot of sulfur.
Right.
We
didn't
didn't
know it, but yes, that's exactly it. We
we
didn't
didn't
have
use
the
it.
strong impact from the warming of the greenhouse gases because the accidental cooling was keeping things okay for a while longer. So we kept burning
Especially
more
where
of
we live,
the fossil fuels. Yeah.
especially where we were burning those fossil fuels and growing our food, and still are, and we are still where we are still, especially in India and in other countries, they are still keeping themselves cool by burning a lot of coal, while warming the planet. So they are making the problem worse very rapidly, like many of us do, but they are also hiding the effects of the rapid surface warming. In the summer, it's about 64 watts per square meters during the day, because it's, of course, that's on average for the day, that's what we learned. What was learned from the data from COVID when there were lockdowns. There was an increase in radiation surface of 16 watts per square meters, but that's on average 24 hours a day for a 24-hour average. On the middle of the day, it's about 4 times that. So that's a lot of additional heat being reflected back to space, and which would warm the surface if you stop emitting. So the problem is being the real problem is being hidden, and that would, of course, if you would do intentional cooling, whether you would do it over the oceans with marine cloud brightening, or whether you do it in the stratosphere, it's really crucial, and I think it will be done because the effects will be very dire. And that's, I think, and it's very cheap.
I agree with you. I agree with you about that.
It will most likely be done, and we should learn from these natural experiments, like what happened now. We should learn, especially to understand how much warming we can expect as we reduce these emissions, and we should also, or the ones doing research on intentionally doing it should also learn from these natural experiments, because you can learn much more of the experiment of reducing sulfur or aerosols over the oceans by 8 million tons per year. Then you can learn from simple experiments with some salt particle emitting snow cannons over Florida or over Australia, where they are doing some small tests. So I think that's also to try to learn from what's there. Try to learn from volcanoes that put particles in the atmosphere, and from ships, and don't use the subject of intentional cooling as a reason not to discuss what's happening right now, or what.
I totally agree. That's the moral hazard argument, that cooling the Earth would give us an excuse to continue to emit fossil fuels. But I say
no, that's not what I'm saying. This is what I'm saying.
Okay.
So this from the IPCC. So what they show is, okay, what happens from stratospheric aerosol injection or marine cloud brightening or other methods of cooling the planet, and they elaborate in detail of what could happen. And they talk about the negative effect of stopping marine cloud brightening, so cooling the oceans by emitting particles, and that could be sustained. Termination could cause rapid warming, abrupt changes to the water cycle, but they don't discuss that in relation to what we are doing already, stopping these unintentional marine cloud brightening. That's not being discussed. Also, the International Maritime Organization, the UN agency that covers the oceans and the shipping, they don't discuss this termination effect, and most climate scientists don't like to talk about it. They don't talk about it. It's in the IPCC reports. It's often being cut, and it's not being talked about. And I call it gross negligence, because there's a duty to inform about very serious risks that could be upon us now that we are reducing this air pollution. And the same is true for India. If India will see rapid warming as they reduce their air pollution from coal plants over the next decade, they should prepare for that. They should prepare for this changes in the water cycle, as I just showed. They should prepare for changes in monsoon, the location where the monsoon rain falls, because that's what some models show, that if you reduce this air pollution, the monsoon will change, and it will get much hotter. So they need to be informed. People need to be informed, and it's always a bit of to me it's a bit difficult because it's the first question people ask. Oh, aerosols cause cooling, so we should do it intentionally, instead of, okay, what happens now if we stop reducing it? First, try to understand what's happening now and adapt to that, and then decide, okay, what are we going to do further with this information? because I think
we're doing the opposite, right? Rather than putting more aerosols up to cool the earth on purpose, we're sort of accidentally reducing aerosols and increasing warming dramatically. And yet,
many are gatekeeping.
If you do it on purpose, or some kind of moral issue, if you happen to do it to clean up for human health, then I guess people ignore the impacts. I mean, we are ignoring it. I mean, you guys are writing about it.
It's not just ignoring. It's some are lying about it, or saying it's there's not, or saying we are lying about it.
Okay.
Many are saying we are lying about it, and for whatever reasons, to sell their books or to be willfully ignorant. But the parties that are responsible for informing the public are not sharing this information either. And
like
now,
the IPCC is the main body.
Yeah, right? But IPCC or the regional weather agencies or climate agencies, or there was a report from the European agency, environmental agency, where of 200 pages of climate risks, where they don't even talk about aerosols, and aerosols are the biggest regional risk. We've seen with climate models that don't take into account the reduction in aerosols underestimate Europe. It's warming by 1 degree Celsius in the summer. That's not, and that's from climate model, but that's comparing these climate models to real world observations. Europe is the fastest warming continent. And if the bodies, the agency that are responsible for informing the public don't inform the public about the biggest risks, that's gross negligence.
So what you're saying is that Europe is warming faster than any other continent, and the main reason you would say is that Europe's doing a great job of implementing climate policies and pollution policies to clean up pollution, and so they're doing a great job. They're cleaning up that pollution, and that is causing a direct effect of increased warming. Is that why you think that Europe is warming faster than anywhere else because of that?
Europe was also the country emitting the most sulfur in the world.
Oh, was it really?
The continent emitting the most sulfur in the world.
Oh, wow. Okay.
So, and then around the 1980s, that was reduced more and more. And now it's at the level of about 1890. So
I think UK just shut down their last coal plant recently or something.
Yeah, and even before that, the coal plants that they did have were using these scrubbers. They used
right, and the US uses those scrubbers too.
Exactly.
To stop acid rain and things like that. Yeah. Exactly.
The limestone. So the churches were made of lime, and they dissolved from this from this acid rain. But now then they took the limestone from Dover, from these cliffs, from these white cliffs, and they put them in the scrubber system. So washing this water with this limestone inside through this exhaust gas from the coal plants, and then the sulfur reacted with this with the lime, and that formed gypsum. And the gypsum is then a product which you can sell on the market for building construction and also you see for agriculture. And then from that period you see that there's much less sulfur being emitted and more also being used in homes and etc. And then that's when the sulfur emissions decreased and warming accelerated, and that's why Europe is now the fastest warming continent, because it was also cooling the most.
Okay. Wow. Anyway, it's been I've learned a lot today, so this is great. And I think we covered all the main points of the update. So what I want to do is turn it to questions first from our co-mods, Stacy and Eli. And if there's anyone in the Zoom audience that wants to ask a question, please raise your hand, use the hand raising function. If you're watching on YouTube and want to join in the conversation on future climate chats, the way you get the Zoom link is by going to our Clubhouse room, which is usually posted on Twitter after I post the YouTube live link. You can find the Clubhouse link. And then if you join there, you get the Zoom link, and that's how you get to join the audience questions. So let's start with Stacy. And Stacy, welcome to the stage here. And what's your question for Leon?
Hi, Leon. Thanks for being
Right.
here. Love your work online and your valiant defense of the state we're in. Um, I'd love to know, I keep saying it doesn't, you were saying about it's a philosophical question. Is it the this or the that? Is it the aerosols, lessening of the aerosols or the increase in GHGs that is causing the problem? I keep saying who cares? Like just do everything. We know the GHGs cause the warming. We know we've taken on this Faustian bargain. Um, what would you do other than, keep it all in the ground to try and change this situation to and hopefully cease this debate and just get GHGs and our temperature lower? Thanks.
You're king of the world, Leon. Or
Doing
the
Yeah.
climate czar. You're the climate czar of the world. What
Yeah.
steps would you take?
So I think it is important, and I said it's in part it's a philosophical question, but of course it's crucial to understand how much India will warm when it reduces its sulfur emissions. So it's not only a philosophical question, and it does matter. Um, and people need to be informed. People in India. So I'm not going to tell India what to do. I'm not going to tell 1.4 billion people what to do and whether they should cause cooling or whether they should adapt or whether they should suffer more, right? Or whether they should close all their coal plants tomorrow and suffer the consequences. That's not up to me. And but the first step is really to take this seriously. People need to be informed. The people building our dikes in the Netherlands need to be informed about how fast the sea levels could rise, taking into account the real world emissions and the real world changes. And people need to be informed that there's more sunlight reaching the surface now. They should use more sunscreen or don't get into the sun because they are not used to this very active sunscreen. I mentioned before that we are now, especially during the solar maximum, there's about 15% more UV radiation. So we are exposed to when there's a blue sky, we are exposed to sunlight that we haven't seen in Europe for over 100 years, and so that it is important. People need to know, and then we need to adjust accordingly. And what we do, that's not up to me. If, if of course we should take this. If you want to cool the planet with whatever method, take into account that you also need to indeed very rapidly need to reduce methane and all the other
Right.
greenhouse gases. Otherwise, you're just making the problem worse. And then if something happens, you cannot emit these particles anymore. The termination shock, will be even bigger than it would be now if you would stop now. So that's really a serious point, because we can say, okay, that will not happen. We can always, some say that we can always keep emitting these particles into the stratosphere. But I wouldn't be so sure about that. You see, if a ship hits a bridge, or if a storm goes through Houston, even one of the richest states in the world, right? There's 1 million people without power for weeks during a very hot summer, or starting summer, and then they don't have AC, they don't have a fridge that work. So it's easy to there's a lot happening, and we've been keeping ourselves blind, or we've been keeping people blind to one of the crucial aspects of the climate system, and that's also gave climate deniers a reason to not understand, and also to keep others maybe ignorant about what's really happening. Because if there's cooling, yeah, so the greenhouse gases are not causing warming, right? If you don't take into account the cooling effect of pollution.
And just an elementary clarification about something you just said. You said that Europeans are experiencing, blue skies, more UV radiation. That Europeans have not experienced this in 100 years. You're saying because the sulfur that is conveniently filtering and reflecting the light back and the heat, etc., is also like our sunscreen too. Like, and so
Your UV
so
sunscreen, yeah.
if sulfur had not been in fossil fuels, maybe we all would have gotten cancer faster and had more people ending that way, and more people might have taken it seriously or something. Just positing.
Although the sulfur itself kills millions of people a year. So I'm sure that's more, well, I'm not sure, but I'm going to guess it's more than who die from skin cancer from the UV because of
so we don't know what are we comparing it to? Indeed, there's air pollution. And that's again what the example of India. Is it worth it for the if I sell it somewhere else before? So of course, from the perspective of air pollution, you should do it. You should reduce this air pollution. But from a climate perspective, I don't know. And I think what we really should start with is reducing indoor air pollution, because there's still a lot of women and mainly women and children, about 4 million dying from indoor air pollution of using biomass to cook their food, including cow dung. I've been in India and I saw people cook their food using plastic and using cow dung, and that's really horrible for your health. So start there, and then take all these aspects very seriously.
Which do people care less about, climate science or public health? I guess is the next question.
Well, the fact that the fossil fuels kill 8 million people a year, the burning, not climate, just the pollution from burning of fossil fuels killed. A Harvard study showed that there's 1 out of 5 deaths in the world. There's no discussion whatsoever of that. It's as if it doesn't exist. And that's kind of amazing, I think. But which, it just shows our ability to kind of look the other way for
turn it off. No, nothing here, nothing to see. Okay.
But anyway, so that's great. Thanks, Stacy. And we're going to turn to Eli now for the next question. If you have one, Eli.
So comment and question. Good to see you, Leon. So first the comment. One example of the consequences of increased sea surface temperature beyond, the devastating effect on coral reefs, which are, a very fragile ecosystem that really matters to ocean ecology and even feeding humans in terms of the role that it plays in fish ecology, is apparently this last year in the main development region, which is the Atlantic Ocean between 20 south and 20 north. The main development is the development of hurricanes. The temperature bottomed out over the winter at a level that is equivalent to the average July or August. Right, and it's only warming up from there. So a very real consequence of this is we are extremely likely to see an extremely bad hurricane season. Hitting places like Florida. This was mentioned. Well, okay, I won't go into that. But the thing that I wanted to raise, you were actually tagged in this. It was a thread by Jeff Berardelli, the meteorologist in Florida. And he was citing aerosols, and he got some of the skepticism. It was actually one of the seemingly better arguments in terms of support, data being shown. What the argument was that actually there is little effect on, or clouds are still reflecting plenty, and there's little effect of these sulfate aerosols on clouds, which of course we know they are important to. And the maps that were shown to support this was a comparison between 2020 and the average since. And the fact is that if you look at just 2019 or going back to 2015, when people started, or shipping organizations started reducing these aerosols, there were already effects on sea surface temperature going back to that, earlier reductions. So I'm wondering, are you seeing, kind of these sophisticated disinformation arguments that on the surface look persuasive, but have like some very basic flaws in them?
Hi, thanks, Eli. Yeah, I'll go back to this Atlantic main development region. So I don't know exactly what you're referring to. I didn't. I might have looked past the message from Jeff, but I've seen somewhere else that so what's happening to clouds is crucial, of course. But what we do is look at the radiation. I didn't mention clouds, because we just look at how much sunlight is coming in and how much is absorbed and how much radiation is going to space. And then in this region, as I showed you, where most of the shipping happened, there was this increase compared to the first decade of this century of 4.3 watts per square meters. That's over the North Atlantic, the North America, and North Pacific combined, that combined region. Whether that's from direct reflection of particles, or changes in how high the clouds are, or how white the clouds are, or how big the clouds are, or how long they last, this data doesn't differentiate between that. We don't really the data doesn't care whether it's a cloud or ice reflecting that. It just shows how much light is going back to space. So, and I don't know, you can of course use a simple model, as I mentioned, to say that there's little warming from this, and that Zeke Housefather wrote a blog about that, and a lot of institutions are just copying this number and saying, look, it's very small, the effect is very small, look at this blog. The NASA director writes an article in Nature, Gavin Schmidt writes, and he says the effect is very small. What citation does he use in a Nature article? Zeke's blog, using which uses estimation of global average reduction. So yes, we see a lot of very sophisticated looking argumentation. I love Zeke's blog on carbon, the website. It looks great, and I provided some data for this article he wrote on shipping. But just taking the summary and the number in the summary of saying there's a very little effect, and everyone just copying it and saying, look, the effect is very small, without looking at the data we present. Yeah, that I think that's not helpful. So that's one. Okay. And then I just can show you the Atlantic development region very shortly. So now already here, this blue line is this year, 2024. Can you see it? Yeah. We are already at the sea surface temperature in the region where these hurricanes develop at the highest ever, about as high as it would reach in September or October. And then last year it was also quite high, but then there was an El Nino, which reduces how much hurricanes form generally. But now we have a La Nina forming. So I would be quite worried if I lived in Florida, or if I lived in the Caribbean, or because we could see very, very, very strong hurricanes forming this year. Of course, you never know for sure. Some things might change, but I would be quite worried, and I don't think it will be easy to get insurance this year in the months ahead.
El Nino causes wind shear that helps keep hurricanes at bay. La Nina does the opposite. So now you have the high temperatures, which feed hurricanes, along with the lower wind shear, which allows them to form. And that's a recipe for disaster. So thanks, Eli. And now we're going to turn to Eric. Eric, welcome to Climate Chat. And what's your question for Leon? You can unmute. You should be able to unmute and turn on your video at this point. Eric?
Okay, can you hear me?
Yeah, I can hear you.
Yes.
Great. Go ahead.
Okay, great. The question is, how predictable is it? Exactly what kinds of terrible things are likely to happen in Florida due to the situation you just mentioned?
Well, I think more hurricanes.
I think that's a good question to ask, Jeff. And of course, the regional meteorologists have the best answer, the best data for what will happen regionally. We look really on the large scale, at the largest scale of all this, and then we see that there's much more heat in the system. And as I just showed, especially in the region where these hurricanes form, there's record amounts of heat for this time of the year, and the conditions are there for. I think that the predictions I've seen are the highest of any predictions ever for amount of hurricanes and also strength of or the amount of strong hurricanes also. And
Great to know.
there's also a lot of unknowns. We've never had a climate like this. When was it last year when this hurricane 5 formed and destroyed Acapulco within a day, which was not
the increase in the strength was like the fastest ever increase in strength. It was crazy,
and no model predicted that to happen. So I don't know. So if you ask me what causes what, I think that's on this scale is very complicated, and it's also how I like to look at it is just from a heat perspective. Indeed, about a million Hiroshima's nuclear bombs worth of heat accumulate in the Earth system every day. That heat, that energy, will impact cities like Houston. So if people ask me, okay, did this wind going through the downtown of Houston, destroying all these buildings, was that caused by climate change? To me, there's a lot more heat in the system. It's like asking if you have a pie in the oven, you switch it on. Is this joule of heat? Is that what did the oven put that in, or was it already in the pie before you put it in the oven? It's a difficult question to answer, and also pretty in a way useless, because you know there's more heat in the system, and that's caused by these greenhouse gases, and aerosols reduce the amount of heat. Like it's like opening the oven and reducing heat, right? So you can give many examples, but we should prepare. If you look at the oceans, if you look at the North Atlantic Ocean, and that it is now half a degree warmer for an average of a year, and that it takes over an area of 40 million square kilometers, and that it takes so much heat, 3,000 times, over 3,000 times as much heat to heat the same volume of water as for air, we should really be worried. And if you live in Florida, do you live in Florida, Eric? No? Okay.
No.
Good for you. But
Is there time for one more, Dan? Probably not.
like a quick one.
Are there any climate models that good computer scientists who are not climate scientists should be leveraging and exploring? And if so, what should we be doing with them to educate ourselves and educate other people?
I recommend
now with things
look
like
at the
Amazon.
Data.
Pardon me?
I recommend to look at the data. You know, you have all, as I mentioned, you can look at the simple models, but these models are wrong, especially if you look at regional effects. These models they don't show what's happening over Europe now. They don't show what's happening over the oceans. So I really recommend to look at, for example, the website from the University of Maine, where you can look at the data quite easily, They have these research tools where you can do monthly reanalysis, and then you can just look at temperatures and what's happening. And also at the data from NASA, which that's what I showed you, where I showed you how much sunlight is coming in, how much is reflected. You can download that quite easily as data, which you can put in Excel or in whatever software you use, and then you can start to try to understand what's really happening in the real world, because the climate models are only models and they don't show what's happening in the real world. They model the world and they try to reproduce it, and they cannot, of course. The data is much, I mainly look at the data, and I think models are interesting, but there's one example I sometimes give is when I was at this European Space Agency seminar over a decade ago. There was this guy giving a presentation. He was really proud of his data, and after a few beers, he was like, "If I want to make it rain, I make it rain. If I want to make the sunshine, I make the sunshine." It's like you can make your model do whatever you want if you understand what changes your model.
But
So
I
that's
think it's
why
important
Maybe
to
you don't
point
get
out
into class in
that.
analyzing the data. Thanks so much.
But I think
Right.
what's important to point out is that the charts that Leon was presenting during this climate chat episode, that was data. That wasn't models. That happened. That was measured changes in the Earth temperature, sea surface temperature, sulfur, emissions. That was measured data. And so we are now at the point where we are measuring the change in the Earth system, not just predicting it. When Jim Hansen spoke to Congress in 1988 and warned us all about the need to reduce fossil fuel emissions rapidly, because he said by the end of the century that the climate change signal would come out of the noise and we would be able to detect it. First of all, he was right about that. But now we're in the realm where the signal is way above the noise. We're seeing the impacts. It's affecting our daily lives, affecting the price of coffee and chocolate and insurance and food. Everything is happening now. It's real, and the effects are not linear. So when we hit 2 degrees, it's not just a little bit worse than 1.5 and 2.5, et cetera. So one of the questions in the chat here on Zoom is, are we all doomed? I would say that the future is still in our hands. I mean, we certainly put a lot of greenhouse gases in the atmosphere that is causing damage today. So avoiding damage is not one of the options we have available to us. But how much damage in the future we suffer from is up to us. And we can do things like dramatically lower our greenhouse gas emissions, something we are not doing. Emissions are still going up, just to be clear. So when we're not really fighting climate change the way we're supposed to be, we need to lower those emissions dramatically. And in a future episode, we're going to talk about my 20-point plan to accomplish that, which is actually very straightforward, by the way. And you'll be surprised that one of the key points is lowering fossil fuel emissions, which is something we actually can do if we chose to. And then we might have to take steps like purposely cooling the Earth temporarily while we take other steps and things like that. So we'll be talking more about that in the future. But I want to just a big thank you to Leon Simons for joining us today, for not only helping us understand James Hansen's very recent update on the global warming the pipeline paper that Leon was a co-author of, but also giving us a much better insight into the data behind how we think we know that shipping is the reduction in shipping emissions is causing a big change in warming, and what the implications of that. It was really I learned a lot today, as I always do on this show, and I just really want to thank you so much for joining us. It made it a far more interesting show. I also want to tell everybody out there watching on YouTube to please subscribe and to like this episode. That will help others see it. Also, you can follow me on Twitter at Dan Miller 999, and that's you'll see announcements of future shows, and again, sometimes a summary of a Hansen update and that kind of thing. So please do that, and please, tell your friends and to also subscribe, and let's build up an audience for this, because this kind of information is really important. And as Leon was pointing out, not everyone is really aware of this. Sometimes ignores or denies this, and we all have to get smarter about it. And so thanks everyone for coming. We'll see you next Sunday. We do it every Sunday at 10 a.m. Pacific time. And we look forward to seeing you next time. Leon, thanks again. Really appreciate your being here. And I'm going to share this slide as we all say goodbye. So thanks everyone, and we'll see you.